Hey everybody, just want to say a couple things about the calendar before I get into talking about the quiz that you've just taken and the lessons to come. I'm going to be covering 3 lessons in the next 4 class days. Lessons 13, 1, 2, and 3 in the next 4 days. That's the next 4 days are oh. Hey everyone, just a couple comments about the calendar before I get into the work for today. I'm going to be covering 3 lessons in the next 4 class days. Lessons 13, 1, 2, and 3 in 4 days. That's Wednesday, Thursday, Friday, and next week Tuesday. I don't care how you pace yourself over those 4 days to get those 3 lessons done, but I'm going to make 2 of the 3 lesson videos available on the very first day, Wednesday, and you can work ahead a little bit if you want, or try to space it out a little bit more. The 3rd video will probably not be available until Thursday, but I'll get them all up as soon as I can, and you can work through them at whatever rate you want. Okay, let's talk about the quiz that you just took, which was assigned either Friday for you or Tuesday. Just a couple comments about the way I solve some of these problems. This regular hexagon problem, I chose not to use the regular polygon formula, which you could use. I chose instead to think of this regular hexagon as 6 equilateral triangles, because all regular hexagons are like that. They're made up of 6 equilateral triangles. So then I did not have to spend any time or energy trying to figure out what the apothem was of this regular hexagon. If the length of one side is 20, that's the length of a side of any one of the equilateral triangles. I've got that formula right there to find the area of that single equilateral triangle, and then just multiply by 6. I really think that's the easiest way to do this problem. If you had done the work to find the apothem, then you should have come up with a value for the apothem of 10 times the square root of 3. That would be the length of that apothem right there. And then you still should get the same answer for the area of the regular hexagon. Number 3, the circle area is very straightforward, pi times 12 squared. The area of this large square, I chose to think of that square as 4 of these isosceles right triangles. Because if I know the radius of the circle is 12, then I know each side of this right triangle is 12. So I have a base and a height for that right triangle, and it's super easy to calculate the area of that right triangle. 1/2 times 12 times 12, but then there's 4 of them. To me, again, that's a lot easier than trying to figure out what the length of a side of the square is, which is not that big of a deal, quite honestly, since this is a 45, 45, 90 right triangle. The length of that side of the square would be 12 times the square root of 2. And then to find the area, you would square 12 radical 2. But in my experience, there are still too many students who are having trouble doing this, or are stumbling over doing this. If you square 12 radical 2, you should get 288, because 12 times 12 is 144. Root 2 times root 2 is 2. And then 144 times the 2 is 288. But I just avoided that work by finding the area of the triangle. Okay, let's turn over the back page, see if there's anything I want to comment on there. Number 6 is another perfect example of one of those kinds of problems where what I'm saying is write down the formula, plug things in the proper place in the formula, do the algebra to solve for the one missing item, and then make sure to double check that when you've finished the algebra, that the answer you've come up with here is in fact the thing that I'm asking for. Solving this, if you didn't get, if you set up this equation and you didn't get this answer for theta, try undoing the operations maybe in a different order than the way you did them if you got the wrong answer. But you've got to be able to do this algebra here. I would start simply by multiplying both sides by 360. That'll cancel out that 360. Then divides both sides by pi. That'll cancel that out. You'll get some ugly number over there. 20 squared is 400. Divide both sides by 400. And then you'll solve for theta. Now, I must have done my work here in a slightly different order. Clearly, I left dividing by pi for last. But whatever. I don't care what order you do the steps in. You've just got to be able to do them. Number 7. Kind of the same thing as number 6. You got to start by writing down a formula, but this problem says an equilateral triangle has the same area as a circle. Same, equal to. So here's my equals. Here's the formula. Well, not the formula, okay? Here's just one part of the formula. There's one side of the formula for the equilateral triangle area. The other side says A equals. And here's one side of the formula for a circle, and the other side says A equals. But those two areas have to be equal to each other. So there's my formula. Plug the 16 in for the length of the side of the triangle. Start doing your algebra, and you're on your way. Now in this case, when I finish the algebra, I do not get the answer to the problem because I've asked for the diameter of the circle. So here's, one of those where you got to double check at the end. Make sure after you've solved the algebra that what you've come up with is in fact what I'm asking for. Okay. And then, since Fernwood Farm has dimensions, Colossal Corporation has a farm which is 25 times the dimensions of Fernwood's, anything that is a function of length is going to be multiplied by 25. The fencing that goes around the cattle is a length measure. I know the fence is surrounding an area, but the fence itself only is a length measure. We're not laying down the fence over the ground. We're just putting it around the perimeter of where the cattle are. Whereas the water has to be spread over the entire area of the vegetables. So the amount of water that Fernwoods use, 4,000 gallons, we're not going to multiply that water by 25. We're going to multiply it by 25 squared because the water that you need is a function of the area of the vegetable plots. And that's an awful lot of water, and that may be surprising. You may have come up with that answer and thought, no way, that can't possibly be right. Well, it is. All right, let's move on to the lesson for today. These are not the notes that I wanted to lay out in front. Well, actually, what is that? That's the handout. I want to make some comments on the handout after we've gone through these notes, but here's the notes for today. Two things we're doing today. The first is surface area. Okay, I don't honestly know if surface area is something that you may have addressed at all in junior high or middle school. I'm sure that you've touched on volume, but this is surface area and it's completely different. Surface area is still area. And so the units, when we get an answer for what is the surface area of an object, will still be square units. Okay? Surface area is talking about three-dimensional objects and finding the areas of all the individual surfaces and then just totaling them up. So this thing we might just call a box in everyday conversation, but in geometry we call it rectangular prism. I'll explain that in just a moment, the meaning of that phrase, why we call it that. It's got 6 different surfaces. It's got a top, a bottom, a front and a back, and a left and a right. We've got to find the area of each one of those 6 rectangles and then just add them all together to get the total surface area. Now, when you hear the word prism, you might think of something that you may have seen in grade school or junior high, something that looks like this, right? That you can bend light through. And so when you hear the word prism, you may look at this and go, that's not a prism. Well, it is. Both of these are prisms. We would call this a triangular prism because it has two triangles that are congruent to each other and parallel to each other, and then edges connecting those triangles. Here, I've got a rectangle at the bottom and a rectangle at the top. They are congruent, they're parallel to each other, and then we have edges connecting those rectangles. A prism, by definition, is a solid object which has two congruent polygons that are parallel to each other. The polygons can be any shape. They can be triangles like here, they can be rectangles like there, they could be hexagons. You could have two hexagons and then edges connecting those hexagons, and you would have what we would call a hexagonal prism. So prisms are not just triangular in shape. Anyway, we got to find the areas of all 6 of these rectangles and add them up. So I've laid out individually the 3 different kinds of rectangles in this prism. Here's the front rectangle. It's 80 by 50, which is an area of 4,000, but there's 2 rectangles like that because the back is congruent to the front. So multiply that 4,000 times 2. There's the top rectangle, which measures 12 by 50, that's 600, but there's 2 of those kinds of rectangles because the bottom matches the top. And likewise, there are a left and right rectangle, each of which is 960. So add this 8,000, this 1,200, this 1,920, and you get your total surface area. We're just adding these areas all up, okay? So each of these rectangles has a distinct set of dimensions. All right, you've got to see that. You've got to do all the calculations correctly, and it really helps me if you show me when you're doing your calculations what your calculations apply to when you're coming up with your final answer. I can't tell you how often I'll give a problem as simple as this, and a student will turn in some work, and here's what I'll see. I'll just see a 4,000 scribbled somewhere. I'll see a 600 scribbled somewhere else, and then I'll see maybe a 1,200, which doesn't match this. Okay, so there's a mistake. I'm forced to assume that the 4,000 came from this. I'm forced to assume that the 600 came from that. Where the 1,200 came from, I have no idea. And then, in their final answer, if I look at their final answer does not come from adding their 3 numbers together. It also doesn't come from doubling each of these numbers and adding them together. So not only have they made a mistake in one of these areas, they've made some kind of mistake in getting the total, but they've given me no clue as to what they're doing. And in that case, I usually give very little credit for their work. They got 3 numbers scribbled and a wrong answer, and one of those numbers is wrong, and I don't know how they're even getting their wrong answer. Show me, make it clear where all of your numbers are coming from. Okay, so diagramming each of the separate rectangles and identifying what each of those rectangles represent. This is the front, this is the top, this is the left. Okay, that will get you a lot of credit sometimes if ultimately you have an incorrect answer. If you make one little mistake here, you're going to get the wrong answer. And if you haven't shown me your work in detail, I have no idea really if you have any idea what you're doing, because I don't know how you got the wrong. You could have made 10 mistakes for all I know. So make that clear to me. Moving down, now we're going to find the volume of this same rectangular prism, the volume of this box. Volume is measured in cubic units. Right? Here's a picture of a cube. So how many of these cubes Suppose these measures are in centimeters, 80 centimeters, 50 centimeters, 12 centimeters. Here's a cube, which is 1 centimeter by 1 centimeter by 1 centimeter. It's 1 cubic centimeter. And so whatever measure we get for this is going to be in cubic units. How many of these little cubes will fit inside this whole box here? And I'm sure you learned a long time ago that the volume of a box is just length times width times height. And since all three of those numbers are being multiplied together, it really does not matter what order you multiply them in. So multiply them in any order you want. But notice the formula I wrote here for the volume of this box. I didn't write length times width times height. I wrote capital B, which stands for base area times height. Now the base of this box, let's talk about that word base. When we talk about a rectangle and we say a rectangle's area is base times height, that word base refers to a length, right? When we're talking about the volumes of solid objects and we use the word base, what is the base of that solid object? In that context, the word base is referring to an area, not just a length. And that's why I use a capital B here. And if you look up volume formulas online, you're likely to see a capital B also for base area. If it was a lowercase b, if I were using a lowercase b, I would mean that to stand for a length. And I have a reason for writing this formula like this. I don't mind at all if you think of the volume of a box as length times width times height. That's fine. But on the next lesson, 13-2, I'll talk about why I like to write the formula this way, base area times height. But we'll get to that in the next lesson. So 50 times 12 times 80 is 48,000 cubic units of whatever kind. Let's go over to the back page. All right, the volume of this object, not as straightforward. This is not a simple box, but it can be split into two boxes. You know, this should remind you of the kinds of area problems that we did, where I gave you a shape like that and asked you to find the area, and you had to split it into two rectangles. And you have, two choices for how to split it up, or you could even think of it as a solid rectangle with a piece missing. So you've got the same three sorts of options here. Now I'm choosing to extend that vertical line straight down, sort of cutting off that back box from this front box. And then that back box has a height of 40, a width of 100, and a length of 22. So multiply those numbers, I get 88,000 cubic units for that box in the back. And then this box in the front has a width of 100. The length of that box from front to back is not 80, because 80 goes from front all the way to the very, very back. But I'm cutting this box off at this point. Well, if that's 22, then that's 22, and that is 22. So subtracting that 22 from the 80, I get 58 for the length of this box from front to back. Okay? And then, of course, we said again, it's 100 wide. How tall is it? I've written it to 10 there. It's 10 tall. How did I figure that out? Well, the whole entire thing is 40 from top to bottom. But from top just down to there is 30. So if that's 30, then that's 30. And that 40 minus that 30 leaves 10 for that very shallow box in front. So 58 times 100 times 10 is 58,000 for the volume of that box in front. Add those two volumes together, you get your total volume. Okay. Now the surface area. Wow, is surface area way more involved than volume. And surface area problems tend to be more involved, involving many more calculations than volume. We've got lots of surfaces in this box. So what I've done here is I've created a bunch of spaces to calculate individual areas. I've created 8 spaces. I don't know how many surfaces. Oh, well, I've said here there's 8 distinct faces of this object. So I created a space for each face. Although I'm not sure ultimately if that's how I calculated it. Let's see what I've done here. Notice I've numbered spaces of this box here. 1, there's a 1, there's a 2, there's a 3, there's a 4. And so here I wrote and circled a 1 to indicate to my teacher, hey, right here in this box, I'm calculating the area of that rectangle on top of the box. By the way, before I say any more about these calculations, I want to introduce the word face to you. When we're talking about solid objects, we often refer to the individual surfaces of the object as the faces of the object. And I try to avoid using the word side of the object because, again, we use that word side very commonly to talk about an edge of a polygon. How long is this side? How long is that side? Okay. So face, using the word face kind of eliminates that confusion about what am I talking about? Am I talking about the length of an edge or am I talking about the area of a surface? So that's the word I prefer to use. So I'm finding the area of face 1 here, which is 22 by 100. And then, let's see. What have I done here? Let's see. Face 1, 22. Okay, face 3, which is here that I've shaded. This is face 3. That's 58 by 100, so that's 5,800. Now, here's what I'm saying right here. The entire bottom of this, I like to think of this as kind of a step stool here. The entire bottom of this step stool. I could calculate it very easily, 80 by 100. That would be 8,000. But I want you to notice something also. Wouldn't the area of the bottom of the step stool be equal to areas 1 and 3 put together? Look at that for a moment. 1 and 3 put together. Right? I mean, suppose that area 3 just sort of got elevated up to be the same height as area 1. Then the entire top surface of this box then, would be equal to the area of the bottom. So anyway, the bottom area is going to be the same as areas 1 and 3. So that's going to be another 2,200 and 5,800. Or in fact, if I had recognized that earlier, it would have been probably easier just to calculate the area of the bottom. 80 times 100 is 8,000. And then say, hey, the areas of 1 and 3 together, whatever they are individually, together they've got to add up to another 8,000. So anyway, here's 8,000 total between areas 1 and 3. Here's another 8,000 for the bottom. Okay? And I could do the same thing with these two faces, 2 and 4, and the entire area of the back of this step stool. The back area of the step stool is 40 by 100. That's 4,000. Whatever these two individual areas are, 2 and 4, they're going to be equal to the entire back face. Well, I calculated areas 2 and 4 individually. 2 is 30 by 100, 4 is 10 by 100. So 3,000 for face 2, 1,000 for face 4, and then the entire back is going to be another 3,000 plus 1,000. I think the trickiest surfaces to deal with are the left side or left face of the step stool and the right face, because those are these L-shaped things. But again, see how I'm diagramming this out for my teacher? Okay? This is the kind of thing you want to do for me. I mean, look at all of these calculations that have got to be done. If you just got numbers strewn around that are the results of calculations, but you don't show me what you're multiplying or adding to get any of these numbers, and then you've got a total, which is the wrong answer and is not even the sum of all the numbers that you've produced, you are so confusing me. You end up getting very little credit for this problem. Anyway, here is the left side, which I've divided into two rectangles. Okay. And the left rectangle, this rectangle's 880, that rectangle's 580. They add up to 1,460. That's for the entire left side of this step stool. And then the entire right side of the step stool has got to be the same as the entire left side. So in the end, add up faces 1 and 3, and then the entire bottom, faces 2 and 4 and the entire back, and then the left and the right, and they will add up to this total. Okay, so let's just take a quick look at the homework for tonight, and then this video will be done. Volume and surface area of these rectangular prisms, very, very straightforward, could hardly be any more so. I'm asking you to include units with your answers. Remember, volume is always in cubic units. Surface area is always in square units. Notice all the lengths in these objects are in centimeters. Okay. Number 3 is a problem a little different from any of the examples that we looked at. It requires you to do what I call applied arithmetic. And I'm not going to say any more about that, but I think most of you will not have much trouble solving that. And certainly when you look up the answer, if you made a mistake, I think it'll be clear how you should have done that problem. Here is a problem just like the last example we looked at. Finding the volume of this block of wood, not that big of a deal because all you have to do is slice it into 2 blocks and find the volume of each one. But the total surface area, now here I am specifically guiding you by asking you to calculate very particular surfaces before finding the total. But really, you don't have to find, if this were a quiz problem, you don't have to find these surfaces in this order, and you certainly don't have to find every surface individually, because again, we've talked about the fact that these 2 top surfaces here, for instance, total up to the entire bottom surface. Okay, and in case there's any confusion here, I've written upper top and lower top. Okay, so this is the upper top surface. That's what I mean by that. This is the lower top surface. These are both top surfaces, right? But that one's higher than this one. So I'm calling that the upper top and the lower top. And likewise, I have an upper front and a lower front. This is what I'm calling a front face, and this is also a front face. But this one's lower than that one. So there's the lower front face, there's the upper front face. Okay? So that's very much like the example we did. Now here's a problem which is not exactly like the last example. There's even more surfaces in this object. There's 10 of them. Okay? And again, I've given you kind of a head start and some guidance with these. The first surface is this top surface, which is, well, you know, that's not just a length times width. You're going to have to figure out how to find that area. But then surface 2, what could you put in surface 2? What do I mean by surface 2? Well, any other surface you want. But here's a tip. Isn't there a surface that is identical to the top surface? I wouldn't repeat those calculations here. Once you got the area of this surface, I would just identify by name the other surface of this object and write down the same number as I got from these calculations. I mean, save yourself, you know, the time of repeating calculations. The outside right, that's what I'm calling this surface right here. And there's a surface that matches that one too. Don't repeat the calculations for that other surface, but name it maybe down here, because over here I'm referring to a different surface, the inside right. Right on the inside, on the right-hand side, that little surface matches this inside left, right? Well, and then there's 6 other surfaces. And I think it would be good for you, again, to sort of name where those surfaces are in this object as you're calculating those individual areas. It's certainly what I'm going to do in the answers that you look up. Okay? So there's a lesson for today. The next lesson, 13.2, should also be available to you today, and you can watch that video and get started on that assignment if you want right after this one, or you could put it off for a day, your choice. But good luck with all this work.